Hello students, this is Machine Elements 2 additional tutorial on gear design. In this tutorial we will see how to find out the RPM of shafts in the drive system and then the force transmitted in each uh, in each stage. So let's consider this example. In this example we have given a gear drive system where identical gears are used throughout, meaning the, the gears that we have here have equal gear T size. Gear 1, Gear 2, Gear 3, they do have equal gear T size. So gear T size is expressed or is specified in terms of either diametral pitch, which is a SI measure, or we can use module to specify the gear T size, which is the SI uh, measure of gear T size. So in this system, 1 kilowatt power is delivered to the input shaft A at 1200 RPM. So this will be transmitted to gear 2 and then through the shaft B and then to gear 3 and finally to the output shaft gear 4. Another information given here is the number of teeth of each gear is specified. So the input gear have 15 teeth and then the driven gear is gear 2 here have 45 teeth and the third gear have 15 teeth and then finally the output gear have 45 teeth. Now with this given information we are required to find out the RPM of each shaft. Here we are going to find out the RPM of shaft B and the RPM of shaft C. The RPM of shaft A is already given, it is 1200 RPM. So based on this number of T's and RPM of the input shaft, we will look for the RPM of shaft B and the RPM of shaft C. And the second question is to determine the torque carried by each shaft, assuming first 100% efficiency, which is an ideal case actually, because due to friction, the efficiency of the gears is technically reduced in practical case. But assuming 100% efficiency means it is an ideal situation. And the second question is assuming 95% efficiency of transmission. So with this provided information, we will find out the required parameters. So let's dive into the analysis part. So as usual, when we solve problem, always we need to list out the given parameters. Here, the diametral pitch is given to be 5 T's per inch. 5 T's per inch. So here we have used British system to express or to specify the gear T size. So it is 5 T's per inch. And pressure angle is given for all gears, it is 25 degree. Because the gears used here are all identical as specified on the problem, their diametral pitch is the same, which is 5 T's per inch. In other way, if the module were given, then the module of all gears provided is the same because it's already said that their gear T size is the same or the gears are identical. So the required things are here to find out the RPM of shaft B and the RPM of shaft C. So if you resketch uh, this gear drive system, it will be like this. So here we do have gear 1, the input gear actually. It rotates with 1200 RPM and it has 15 number of these. And this is gear 2, the driven gear, and it has RPM of and it has the number of T's equal to 45. The RPM is going to be determined. And here is gear 3, the driven gear, the driver gear now. And then this gear 3 drives gear 4. So the number of these for gear 3 is 15 and the number of these for gear 4 is 45. Now to find out the RPM of shaft B and shaft C, we need to find out preliminary values which are important in finding later the RPM and also the force transmitted and overall gear ratio. Okay, let's find out these preliminary values. So let's start with the diametral pitch. Diametral pitch is the number of teeth divided by the pitch diameter of the gear. This is in terms of British unit. Gear T size specified in terms of British unit. So number of teeth is dimensionless actually, but the diameter is in terms of inch. So here diametral pitch is number of teeth per inch. So if you solve for the diameter, then you get this expression. So the diametral pitch for all gears is the same because the gears are identical. So here we do have, for example, for the first gear, if you want to find out the diameter of the first gear, it's going to be the number of teeth of that gear divided by the pitch, the diametral pitch. So number of teeth for the first gear is the pinion gear, which is 15 divided by 5, and then you get 3 inch. So 3 inch is the diameter of the first gear or the input gear. If you convert this one into millimeter, then you need to multiply it by 25.4 and then you get 76.2 to be the diameter, the pitch diameter of gear 1. Similarly, for gear 2, the diameter of gear 2 is provided by number of teeth of that gear divided by the diametral pitch. Don't forget, diametral pitch is the same for all gears because it's given that uh, the gears are identical. Not only here in this case identical, but always two gears which are in mesh, which are engaged, they should have same gear T size. They should have same gear T size. That means the module of the driver gear always should be equal to the module of the driven gear, or you may say the diametral pitch of the driver gear is same as the driven gear. So if you calculate the diameter of that second gear, it is number of teeth divided by the pitch and it's going to be 9 inch. Conversion to millimeter, you just multiply this 9 by 25.4 and then you end up with 228.6 millimeter. So this is the diameter for the second gear. So this is for the first stage. So gear 1 and gear 2 constitutes the first stage and gear 3 and gear 4 constitutes the second stage. So as already specified, because the gears are identical, then the third is the driver gear, same as the first gear, D1. So D3 is equal to D1. And the fourth gear, output gear, is same as the output gear means it is a driven gear, same as the driven gear 3. I mean, driven gears 2. So this time then we are done calculating the diameters of each gear. It's not as good, but if you wish to find out, for example, the gear T size in terms of SI unit, if you want to specify the gear T size in terms of SI unit, then uh, we can follow this process. So diametral pitch again is given by number of teeth divided by the diameter of the gear, and module, this is teeth, number of teeth per inch, and module is the diameter divided by the number of teeth. That means it is millimeter per millimeter per tooth, and P is teeth per inch. So if you relate the two equations, then you see that the module is the reciprocal of diametral pitch. Module is the reciprocal of diametral pitch. But don't forget diametral pitch. This P is uh, in terms of T's per inch. So you need to convert it to millimeter because module you need to convert this P to uh, millimeter because M is always in millimeter per tooth. So conversion to millimeters, you just need to divide by 25.4 by p-value, then you get m in terms of millimeter per teeth. So here p diametral pitch is given to be 5. So if you divide 25.4 by 5, then you get the module of the gear teeth to be 5.08. So here m is the SI measure of gear T size, and this capital P is the British unit, the British system of gear T size. So this is how we specify gear T size in terms of British unit or British system, and this is how we specify gear T size in terms of uh, SI system. Now we can calculate the RPM of the shafts like this. So let's consider for that the first stage. The first stage of this gear drive system is composed of gear 1 and gear 2. So gear 1 and gear 2 constitutes the first stage. So velocity ratio of the first stage can be specified as the ratio of the driver as the ratio of the speed of the driver gear to the speed of the driven gear. We do have here a minus sign because the two gears are external gears. So the speeds, the RPM of the two shafts is different, or the speeds of the two gears are different. So in the problem, it's given that this one, gear 1, rotates in the counterclockwise direction. So gear 2 will correspondingly rotate in the clockwise direction. So the two speeds are in opposite direction. So the two speeds are in opposite direction. That's why we have here a negative sign. So this is RPM of the driver gear. This is RPM of the driven gear. Or still velocity ratio can be expressed as the ratio of the diameter of the bigger gear to the diameter of the smaller gear, or the diameter of the driven gear to diameter of the driver gear, or in terms of number of T's also can be expressed the velocity ratio. So in this case, number of T's of the driven gear to number of T's of the driver gear can also be can also provide us the velocity ratio for that stage. So here I prefer to use the relation between speed and number of T's. So if you cross multiply these two, then you get RPM of shaft to be like this. So here N1 is the speed of the driver gear, or the speed of the pinion, or the speed of gear 1, which is 1200 RPM. The number of these of the driver gear is 15, and number of these of the driver gear is 45. Then you get RPM of the second gear to be negative 400 RPM, or you can say 400 RPM in the clockwise direction. In the clockwise direction, the minus sign is substituted with clockwise, the word clockwise. So this is the RPM of gear 2. Now gear 2 and gear 3 are mounted on the same shaft. They are mounted on the same shaft securely. So shaft B also rotates with the same speed of gear 2, which is 400 RPM. So generally, the speed of gear 2, shaft B, this shaft B, and gear 3 is equal to negative 400 RPM or 400 RPM in the clockwise direction. 400 RPM in the clockwise direction. Okay, once we get these values, then we can determine the RPM of shaft C or the RPM of gear, uh, the RPM of gear 4. This is gear 4. So how do we find out this one? Let's consider the second stage velocity ratio. Again, velocity ratio for the second stage is expressed as the RPM of the driver gear to the RPM of the driven gear. So in this case, gear 3 is the driver gear, which is P_N, and gear 4 is a driven gear. So the speed of the driver gear, which is N3, and over the speed of the driven gear, which is N4, will give us the velocity ratio. Still, we do have here a negative sign. Why? Because the two gears are external and they rotate in different direction, in opposite direction. So let's now here point out gear 1 already is proved to or given to be to rotate in clockwise direction. Gear 2 rotates in clockwise direction. Now, because the speed of gear 2 shaft B and gear 3 are the same, gear 3 also rotates in the clockwise direction, which makes gear 4 rotate in the counterclockwise direction. In the counterclockwise direction. So the velocity ratio again can be expressed as the ratio of the diameter of the driven gear to the diameter of the driver gear, or in terms of number of teeth, the number of teeth of the driven gear to the number of teeth of the driver gear. So I prefer to use again make a relation between the speed and number of teeth, then I end up with this expression. So speed of gear 4 is equal to the negative of the speed of gear 3 multiplied by the ratio of the number of teeth of the driver gear to the number of teeth of the driven gear. So already N3 is known, it is 400, so you substitute 400, but N3 is negative, so that's why I put here negative sign. So finally here I got the RPM of the output gear, which is gear 4, to be how much? 133.3 RPM positive value. That means this gear rotates in the counterclockwise direction. It rotates in the counterclockwise direction. Now, let me remind you one thing here again. It's given that the gears are identical. So the purpose of making or using identical gears on each stage is to make the input shaft, in this case shaft A, collinear with the output shaft C. In addition, it facilitates the machining of the housing of the gear. Making or using identical gears on each stage helps in machining of the housing of the gear teeth. So you can see this thing clearly on this diagram. Input shaft A is collinear with output shaft C. Why this happens? Because we used identical gears on each stage. Identical gears means, don't forget, the gears that have same gear teeth size. That means the pitch, diametral pitch for every gear here is the same. P, it is 5 for all gears. Or in terms of module, they do have equal module. So this gear has M module, then the corresponding gear have the same module M. So module, we already found it to be how much? It is 5.08 millimeter. So this is a thing that you need to notice here. The next question is to find out the torque carried by each shaft. So let's see how we find out this thing. But don't forget that power and torque are related in such a way. Power is equivalent to the torque multiplied by angular speed. So this is how you relate power to torque. So if you solve for the torque, then power divided by omega gives you the value of the torque. Okay, let's proceed finding the torques now. The torque on each stage. So here we are going to find out the torque carried by each shaft assuming 100% efficiency. That means here the same power flows throughout the gear drive system with no loss. But in practice, we know that this thing can never happen because there is always friction, and due to that friction, we lose some power. So the first case is finding torque assuming 100% efficiency means it's an ideal case. It is an ideal case. So let's find out first torque transmitted with an assumption of 100% power transmission. So here is the equation of the torque. Here is the equation of the torque. So for shaft A, torque on shaft A is given by the power divided by the angular speed of shaft A. Angular speed of shaft A technically is equivalent to RPM of gear 1 or omega 1 you can say. When you use this equation, don't forget that always P is in terms of the unit of P should be in watt and the unit of omega should be in rad per second. In rad per second. This is the right way to use uh, this equation, and then you get finality A in terms of Newton millimeter. In terms of Newton millimeter. But here omega A is already found out. It is equivalent to it's given to be 1200 RPM. So we need to convert this RPM to radians per second. So for that, you can use this equation, pi multiplied by RPM of that gear divided by 30. So RPM of that shaft is given to be 1200 RPM. So if you calculate the value, then you get the speed to be under 25.7 radians per second. So the power transmitted through the gear drive system is given to be 1 kilowatt. So we need to convert kilowatt into watt. So here I multiply 1 by 10 raised to 3 to convert it to watt. So this is in watt now. And then omega is in terms of radians per second. It is 125.7 radians per second. If you substitute, you get the torque on shaft A to be how much? 7.96 Newton meter. Now we are done finding torque on shaft A. For shaft B, we follow the same procedure, but here shaft B rotates at RPM of 400. It rotates at RPM of 400. So 400 again should be converted to radians per second. So if you convert 400 RPM to radians per second, you get it to be 41.89 radians per second. So you substitute back this omega into this torque equation. So torque power is equivalent to uh, 1 multiplied by 10 raised to 3, which is, that means now in watt, divided by the speed, then you get the torque on shaft B to be 23.87 Newton meter. This is how you get torque on shaft B. Concerning shaft C, we follow the same procedure, no difference. So, but shaft C in this case rotates at 133.3 RPM. We need to convert that value to radians per second. So we use the same equation, and if you calculate that, the value, then you get the speed, angular speed of shaft C to be 13.96 radians per second. So if you substitute back this value in terms of the power, power is unchanged because we are assuming 100% power transmission. So conversion of power to watt, then you have omega to be 13.96. If you substitute, you get the torque on shaft C to be 71.62 Newton meter. So through the process, I think you have noticed that the speed, when the speed gets slower, then the torque gets higher. The torque gets higher. That's what the purpose of this reduction gearbox is. So this is these are the values of the torques assuming 100% power transmission. Now we are done finding the torque transmitted at 100% efficiency. But in reality, this doesn't occur, so there is always loss of power through the drive system due to the friction that occurs between the gear teeth. So for that, let's calculate the torque transmitted to each shaft, assuming, for example, here 95% efficiency. For that, the torque on shaft B at 95% efficiency is equal to the torque on shaft B at 100% efficiency multiplied by 95%. So if you do so, you get the torque transmitted to shaft B at 95% efficiency to be 22.68 Newton meter. Similarly, for shaft C, the torque transmitted to shaft C at 95% efficiency is equal to the velocity ratio of the second stage multiplied by the torque transmitted to shaft B at 95% efficiency multiplied by 95%. So if you do so, the velocity ratio second stage means it is number of teeth of the driven gear to the number of teeth of the driver gear multiplied by the torque that we have on shaft B at 95% efficiency multiplied by again 95%. If you do so, you get the torque transmitted to shaft C at 95% efficiency will be equal to 64.64 Newton meter. So this is how you find out the torque transmitted to each shaft assuming 100% power efficiency and assuming 95% efficiency. Don't forget, 100% power transmission in a gear drive system is ideal. In practice, there is always loss due to the friction that occurs between the gear teeth. That's why we have here lower values uh, with an assumption that there is 95% efficiency of the gear teeth. The other thing that we need to find out in gear design is the force transmitted on each stage. So in the problem we are given that this gear 1, the driver gear, the input gear rotates in the counterclockwise direction. It's given. So when gear 1 rotates in the counterclockwise direction, then gear 2 should turn in the clockwise direction. This happens because this gear 1 applies a force to the right direction like this. So this force WT12 tends to rotate gear 2 in the clockwise direction. And then the other force that is applied on gear 2 is the radial load. So we call this one radial load, which tends to bend the shaft. So this is the pressure line. So phi is here the pressure angle. This is how we put the free body diagram for the gear. So due to action and reaction, the same forces tend to act on gear 1 like this. So this is the complete free body diagram for the gear drive system. Now let's find out the force transmitted on this stage. So torque on shaft A is given by this force transmitted Wt21 multiplied by the lever arm, meaning the radius of this gear. If you do so, then you can see that the force transmitted Wt21 is equal to twice of the torque divided by the diameter of uh, the gear. If you do so, you get W2T1 to be 208.92. So the equal and opposite force will act on gear 2. So it's here WT12 is a negative of WT21, which is equal to negative 208.92. This is the transmitter load on the first stage. So this force is responsible to drive the driven gear. And to calculate the radial load on this gear, we know that the radial load is equal to the transmitted load multiplied by tan of the pressure angle. Pressure angle for this gear drive system is going to be 25. So if you substitute the value, then you get the radial load to be 97.42. This is how we calculate the torque, the force transmitted on the first stage. To calculate WTT1, you may also use this. You may consider also gear 2. It's possible to use gear 2. That means, for example, torque on shaft B is equal to the transmitted load to WT12 multiplied by D2 diameter of gear 2 divided by 2. From this expression, you can calculate for the transmitted load. So either you can consider gear 1 or gear 2 to calculate the transmitted load. In this case, I prefer to use gear 1 to calculate for the transmitted load. So both way you get the same answer. Let's find out force transmitted on the second stage. On the second stage, we have gear 3 here, the driver gear, and gear 4. So gear 3 is found out already to rotate in the clockwise direction, which makes gear 4 to rotate in the counterclockwise direction. Why gear 4 rotate in the counterclockwise direction? Because this gear 3 applies a force called WT34 to the right direction like this, to the right this direction, on this direction like this. So this force tends to rotate gear 4 in the counterclockwise direction. So the opposite force will act here on gear 3. Radial forces, they are equal and opposites like the transmitted load, and this is how we put the pressure line. This is the pressure line, and this is the pressure angle. So the transmitted force on this stage can be calculated by considering gear 3 or by considering gear 4. So here let's first consider, let's find out force transmitted by considering gear 3. So on gear 3, this WT force 3 multiplied by the lever arm, this is the lever arm, which is D3 over 2, gives you this expression. So if you substitute, you get the force transmitted on the second stage to be 595.8. So this is the force that gear 4 applies on gear 3. Or if you want to find out the force that gear 3 applies on gear 4, it's simply the negative of the force that's applied by gear 4 on gear 3. So you get the same answer, which is negative but 595.28. Or if you prefer to consider gear 4, then you write the expression like Tc equal to this force applied, which is WT34 multiplied by the lever arm. In this case, the lever arm is the radius of gear 4, which is D4 over 2, multiplied by D4 over 2. From this also, you can calculate the value of force transmitted to gear 4. That means force applied by gear 3 on gear 4. So whether you use this one or this one, you get finally the same answer. Concerning the radial load is simply the transmitted load multiplied by tan of the pressure angle. If you substitute the values, you get the force applied on the force applied by gear 4 on gear 3 to be 277.58. And if you wish to find out the force applied by gear 3 on gear 4, it's going to be the negative of the force applied by gear 4 on gear 3. So you get same answer but in opposite direction, which is negative 277.58. So this is how you determine force transmitted on each stage of a gear drive system. One last thing is how to calculate the overall gear ratio for such gear system. The overall gear ratio for this for such gear system. Overall gear ratio, or so-called gear ratio, is simply the ratio of the product of the driven gear teeth divided by the product of the driving gear teeth. So here is gear 1, don't forget this is gear 2, and this is gear 3, and this is gear 4. So in this situation, gear 1 and gear 2 are the driver gears. I mean gear 1 and gear 3 are the driver gears, and gear 2 and gear 4 are the driven gears. So product of the number of these of the driven teeth means it is N2 multiplied by N4. Product of the driving gear means it is N1 multiplied by N3. So if you do so, you get the overall gear ratio of the system to be 9. Or gear ratio can still be determined by considering the speed. So gear ratio in terms of speed is equivalent to speed of the first gear, gear 1, to speed of the last gear, or speed of the input gear divided by speed of the output gear is also possible. So speed of the first gear is 1200 rpm, and speed of the output gear is 133.3. So if you divide, you get the same answer. So you can follow either of the two procedures. But what is the meaning of this one? Let's say here we said that the overall gear ratio is 9. That means that means here the speed of the input gear is reduced by a factor of 9. That means if the input shaft has 200 RPM, then the output shaft is going to have RPM of 1200 divided by 9. Or in terms of torque, the input gear have a torque of, let's say, TA, and then the output gear is going to have a torque which is multiplied by 9. So the output gear that have a torque of Tc, which is equal to 9 times of the input torque. So force torque is amplified, and whenever the speed gets slower. So that's what we have. So uh, this is the general meaning of, or the general meaning of the overall gear ratio. Okay, if you have any questions, you can consult me at office. Thank you for your attention.